In this lesson, we're going to look at diffraction grating, which is carried on from the double slit experiment, which we have learned in the previous video. So in this part, we're going to understand what is a diffraction crystal, what's a diffraction, and what is diffraction grating. So the questions in A levels are going to be categorized by two diffraction methods. The first one is simply double slit, which deals with AX equals to lambda D. And the second type of questions actually deals with this diffraction grating, which has a formula of n lambda equals to d sine theta. In this lesson, we're going to see how to use the formula and solve some questions regarding this as well. So in a double slit, we saw that if we pass the same wavelength of this same wave through these two paths, through these narrow paths, it diffracts and bends while passing through the narrow gap, right? In this situation, what we're going to do, what if we increase these two narrow gaps to, let's say, 500 or 1000 or 2000? What will happen then? So to achieve that, we have a crystal that has lines on it, okay? Basically, in this formula, D is what's actually going to create problem or trouble for the students to figure out. So we are going to discuss D first. So let's say this is the crystal that we have, okay? And it has very thin lines drawn on it like this. And of course, they are very high in number. They are going to be 500, 300, 1000, 2000. So D is basically the distance between two spacings. So what happens is that when light actually comes to this point, it has actually arrived in this before the crystal. It is a laser, but we know that it is arriving with flat wavefronts like this. So what's going to happen to the light wave when it passes through these narrow gaps? So we know that when the light actually travels through these narrow gaps, it actually becomes circular in nature. So previously in double slit, we only had two openings through which we received these circular wavefronts. Now we have approximately, let's say for the simple case, 500 openings or 1000 openings. What's going to happen then? So to understand this and to simply consider the distance D in the formula, we accept D as a distance between two openings or two sides out of these 500. We want to know the distance between the two spaces. Now, this can be done easily and very simply by a ratio method if we employ that. So how this D is generally given? They give the value of D as, let's say, 500 lines per millimeter. What does this mean? It means that if this crystal was 1 millimeter long or 1 millimeter thick, there will be 500 lines on the crystal. So we want to find the lines between two crystals. So we take lines, ratio the distance between them. So in 1 millimeter, we were able to create, let's say, 500 lines. So how many distance or how much distance is for one line or between one line? So when you figure this out by cross multiplication, you will end up with the value that this small d, which is between two lines, is actually going to come down to as 1 millimeter being divided into 500 spaces, which is what it looks clearly. Okay, so 500, 1 millimeter cut into 500 different levels, you will find out what's the space between them. Okay, so this is going to be D. So my general recommendation to the students is that when you find that this is what's given to you, just simply take this as this reciprocal. So if he had given you, let's say, 2500 lines per millimeter, simply take this in the numerator and this in the denominator. So this is going to look like 1 into 10 to the power minus 3 and then divide this with 2500. This ought to solve the questions very quickly. Okay. All right. So this is the first thing. And the second thing is about what the diffraction pattern actually looks like. This is what the diffraction pattern looks like. It is very similar to the double slit experiment, but in this case, we understand that it's not double slit. It is at least 500 or 1000 slits. So this is what the experiment is going to look like. So we are introducing a laser. The light spreads out exactly because of diffraction and interference pattern. So wherever we see the light, here interference is taking place and constructive and destructive interferences are going to exist between them. So what are these variables in this formula? So n lambda equals to d sine theta. We've understood what is d in the previous example. Wavelength is lambda. Simply put, whatever is the wavelength of the laser or the light, n is going to be called as the order of diffraction. Order of diffraction. And sine theta is the angle from zero order like from the very center. Now, what do we see on the screen because of this? So we have a crystal in front of us with 1000 lines. We introduce a laser light and we see a pattern on the screen that is going to go something like this. So we have central bright fringe that is at order 0. We see a first order bright fringe at order 1, which is going to exist on both sides. Then we see a second order bright fringe, n equals to 2. Over here, this is n equals to 2. So we understand the order of diffraction in terms of the bright fringes that are going to be moving away from the central point. Okay. And the second thing is about the angle. Where is this taken from? This is going to be taken from the 0 order, which is at the center. So this will be theta for n equals to 1. This will be theta for n equals to 2. So every angle has to be measured from the 0th order. This is important in some questions. Okay. So now we just put in the values and see what's going to happen. And one more thing, diffraction of white light is a bit different. You see, the very first time it diffracts, the central line is 0 order. This whole second pattern is actually first order. Over here, this is also again first order. Please be advised that once you move away from this, because they're going to be wavelengths from 400 to 700. And for all of them, this is going to be considered as order 1. Now, when you move away from this, most definitely, after a very short time, after a very small angle, you'll find that this pattern starts repeating again. It starts from the purple line as it did from this point. It starts from purple and then immediately goes to red. So it goes to red like this, and it will be spread out like this one, exactly this one. In that situation, we will take this n to be 2. So please don't be confused by the order. If you're just dealing with one wavelength, just one lambda, then this is what you're going to see. Now let's see where those orders are and where can we simplify them, where we can visualize them. So this is the screen where we're seeing them, and this is where you see them on the screen. There will always be a central bright fringe, bright order, which is at this point, which is actually an order 0. So this is actually n equal to 0. On the other side, this is actually n equals to 1. This is n equals to 1. This will be n1. This will be n1. And the further you move away, this will be n2. This will be n3. Now notice that from the central bright fringe, that is this one, if you move away, this will be theta 1, this will be theta 2, and most definitely this will be theta 3. And on the other side, the angles are exactly the same. That's why the ratios and the answers are going to go on both sides. So this is n equals to 2, this is n equals to 3, right? And similarly over here, this is n equals to 2, this is n equals to 3, n equals to 2, and n equals to 3. Now, if it had been done with white light, then rest assured, this whole sector will start from violet and end at red. And of course, the colors, intermediate colors in between, with orange, yellow, blue, and violet coming over here. So this whole pattern will be referred as n equal to 1. Similarly, when the pattern repeats itself, this whole section will be called as n equals to 2. So white light is special in this regard because it diffracts and gives you a prism effect, right? Okay. So this is for white light, and if we were dealing with just one single light, this is what you will see. Let's apply the formulas and let's see what happens. So this is again a diffraction of white light. You can see that we observe a central bright fringe at n equal to 0. Then there is a spectrum at n equals to 1 on both sides. This is n equal to 1. And then we come to this conclusion that most definitely we will see another pattern starting from violet, blue, and ending at red at this point if the screen was long enough. So this whole sector will have an order of 2, just like when if it was done with a single wavelength. This is what it's going to look like. Okay, so one question that is generally asked in this scenario sometimes, that why violet is seen first, why do you see that first, and why do you see the red later? Why is that the case? See, that is interesting in terms of mathematics. You see, violet in terms of the central fringe, this angle theta is smaller if we were comparing with this red. So when we go up to red, this angle theta red is much larger than theta violet. Why is that the case? So for that, since we are dealing with the first order, we're going to use the formula n lambda equals to d sine theta. We understand we're using the same crystal. So the crystal has same number of lines, even for violet, even for red. So we're going to remove that from the scenario. And since we're dealing with the first order, n will also be cancelled in the comparison. So what we're left with is simply lambda being proportional to sine theta. We understand that red, for example, red has a wavelength of 700 nanometers. So when the lambda increases, the angle also increases. And we understand that violet or blue has a wavelength of 400 nanometers, right? So when the wavelength decreases, the angle also decreases. So smaller lambda, smaller angle. That's why sine theta, or the angle of violet, is smaller than red, and that's why you will see violet first and red later. That is what's going to happen. Even when you repeat the pattern, you will see violet first for the second order, and then you will see red later for n equals to 2. And of course, all the colors in between that are represented over here. Let's try to solve the questions. So over here, it has given you 70 degrees. To confuse you, we know that we have to take it from the central fringe. This angle will be 35. He says that this is actually the first order. So this n is equal to 1. This is what is required. He asks you to find out the wavelength. So use the formula n lambda equals to d sine theta. Over here, the d is already given to you. You can pause the video and see the question yourself. I'm just moving a bit faster than to solve the question. You can pause the video and try it for yourself. So n is given to you as the first order, so n equals to 1. Angle is 70. I'm going to take 35 because it's from one side. Lambda is required, so lambda will be made subject. So d is 1 into 10 to the power minus 6. Sine of 35. Divide this with 1, as n is going to go over here. So lambda comes out as 573 point something, which is, I think, 573.5. So that is going to be option C, 574 lambda. Okay. All right. Moving on to the next question, we have a parallel beam of light has 450 normally on the diffraction grating crystal. So this question is going to be about n lambda equals to d sine theta. Has 300 lines per millimeter. This is the d that we were talking about. This is the value of d. This is lambda. Okay. He says, what are the total number of maxima? Okay. So one new term over here. These points where you will see the light are going to be called maxima because they are constructive interference. And the points where you see dark bands, you will call them as minima. Okay. So let's calculate that. Now, since he's asking us, what's the total number of maxima? That means we are expecting largest possible answer. So considering the crystal over here, light laser introduced, if I had a screen all around, what is the worst that could happen? What is the maximum that could have happened? So n equal to 0 would most definitely as a starting point. And what if this n actually goes to 90 degrees? Most definitely this is not possible. Most definitely we know this. But what if this was the case? So when he asks you the total number of maxima, we are going to put sine as 90 so that it becomes 1. What's the worst that can happen? So let's see that for this question. Okay. How many number of orders are going to be on one side? So n lambda equals to d sine theta. So n is going to be the subject of the formula. This is what I'm trying to find out. So d is already given as 300 lines per millimeter. So the shortcut was millimeter in the numerator and the number in the denominator. Sine theta is 1. So this whole fraction is being divided by the wavelength, which is 450. So this is going to be 450 into 10 to the power minus 9. Now, when you solve this, you get n equals to, you can put in the values and try this for yourself. So when you solve this, you get an answer of 7.4, which means that at this point, the n should have been equal to 7.4, but we can't do that because orders are going to be an integer number. So, and you're always going to round it down. Even if this was 7.8, which means that this is it's 7.8. This is not possible. It can only be an integer. It can only be a 7 or an 8 complete. So we round this down always, right? Okay, so we round this down to 7. This will become 7. So that means that on one side we have 7 orders. So n1, n2, n3, 4, 5, 6, 7. 7. So 1, 2, 3, 4, 5, 6, 7. So 7 on one side and 1 on the center, then 7 on this side. 1, 2, 3, 4, 5, 6, 7. Right? So this is 7 starting from 1. So 7 on one side 7 on the other side, and 1 at the center. So this will become 7 plus 7 plus 1, which is 15. Students generally ignore the central fringe. That is also a bright fringe. It starts from there. So this 15 will be the answer. Now, one more thing. We found 7.4. Let's rerun this example in reverse and try to do the question again. What's going to happen? Let's see what happens at 7. So we're going to try the question again. So this is n lambda equals to d sine of theta. I want to find the angle. That if this n is 7, what will be the angle from the center? And you will notice this is not 90. So 7 into lambda is 450 nanometers, power minus 9. D is already given to us as 1 mm divided by 300. And then over here, we have a factor of sine theta, which will be taken on the other side for the inverse. Okay. All right. So the answer of theta comes out as 70.9, which is, let's take the 71 degrees. What does this mean? It means that at best, this n equals to 7 is actually 71 degrees from the center. And it couldn't even go to 90 degrees, and it has reached its limit. So that is how you visualize the question. Okay. All right. So this question is going to require, okay, so this question is about double slit. The formula is going to be AX equals to lambda D. He says wavelength is this, fringe separation is this. He says what's going to be the fringe separation? The question is about finding X. If the wavelength is now changed to 400 and the slit separation is doubled, yeah, it means that A is being doubled to 2A. So one thing that is constant in the system, let's rewrite this, AX equals to lambda D. What are they not changing? They're not changing the D. D was the distance from the screen. So let's make D the subject of the formula. Take lambda over there. AX over lambda equals to D. And of course, D equals to the new situation where we have AX over lambda. So let's replace the values for both situations. Of course, over there, the D will also be the subject. So A will be left as it is. X was 4 millimeters as given in the question, and the original situation, it had 600 nanometers. Let's not convert the prefixes right now. Let's focus on the variables. This is what we want to find out in the new situation. Divided by the new wavelength is 400. Yes. So 400 nanometers. This nanometers and nanometers will be cancelled out from both sides, so don't need to convert them. Leave millimeters over here because our answers are also in millimeters. No need to convert that either. A gets cancelled out because it has been doubled, right? So A and 2A are going to be picked on over here. Now let's rearrange the situation. So this 2 is going to come down and this 400 is going to go up. So our X actually becomes equals to 400 multiplied by 4 millimeters being divided by 2 into 600 nanometers. Nanometer has been cancelled. So when you solve this, let's keep this millimeter on the outside. So this X comes out as 1.333. Okay. And millimeters was on the outside. So this answer is option A. Last question. So again, this question is about diffraction grating. It's mentioned, so I'm going to use n lambda equals to d sine theta in my system. So he says orange light is 600 nanometers and its fourth order diffraction coincides or matches with the blue light of the fifth order, which means that if they match, it means that their angles are going to be same. What does that mean? It means that if we were dealing with, let's say, orange color on the crystal, let's say we introduce orange color, and on the screen, this is the central fringe, 1, 2, 3, 4. So N4 of orange color matches with the fifth color of blue or violet, which is mentioned. Blue line, right? So 1 at 0, right? So 1, 2, 3, 4, 5. So N is 5, exactly same for orange, which means that the theta angle from the center is exactly the same for both of them. This is the common point where we're going to use it. So let's form the equation for both of them. So n lambda equals to d sine theta. Since I know that angle is going to be same for both of them, and we are not changing the crystal as well, so it can be compared to the new situation. So this side, I'm going to deal with the orange color, and on this side, I'm going to be dealing with the blue color. So d sine theta is exactly same for both of them. So let's replace the value. So n lambda equals to n lambda. So over here, we have the fourth order of the orange color, which is 600, equals to fifth order for that lambda. I'm not changing the millimeters, nanometers over here, because this millimeter will cancel out with this one, and this nanometer is required for the wavelength. Now, when you find the wavelength, of course, 5 is going to get divided over there. You're going to get an exact answer of 480 nanometers. This is the answer of the question. That is how you visualize diffraction. That is how you tackle the questions. You can see the animation for this as well. So you see how the screen is behaving over there. If you take the screen away, the distance between them increases. And you will also see the colors, I think, changing in this animation. You see we're changing the colors from violet to red, and they spread out at a larger angle. At violet, they shrink together at a smaller angle, which I explained just now that why is that so? Because red has a larger wavelength, its angle will be larger. Okay? All right.